Hello, everyone. We're going to be talking about metabolism, energy, and enzymes in this chapter. The main focus is going to be on enzymes going forward. We're going to see a lot of enzyme reactions in cellular respiration and photosynthesis. So it's really important for us to understand what enzymes are. Now, the beginning of this chapter in the book talks a lot about energy, and we do need to know a little bit about energy going forward. But a lot of this is like middle school stuff, so you should understand it. And it's just a really quick review. I don't have you write any of it down, but it's just, again, a quick review. So remember that energy is just the ability to do work. This is what gives our cells just the energy to and the capabilities to carry out cellular processes. The difference between kinetic energy and potential energy, as you can see here, kinetic energy is the energy of motion, it's moving, and then potential energy is just stored energy. We're going to see that in specific foods that we eat, and then we're going to transfer that energy into other potential energy in the source of like ATP. Two different laws you got to know about. First law of thermodynamics. This law states that energy cannot be created or destroyed. Same with matter. It just can be transferred from one thing to the other. It's also known as the law of conservation of energy. And the second law of thermodynamics is within a reaction, there's going to be less energy available in their after reaction than there was before. This is because not every reaction is going to be efficient or 100% efficient at transferring that energy. You're going to lose some of that energy in the form of like things like heat and friction, but you're not going to get as much energy out as you can put in. So again, kind of understand those two concepts. I wouldn't be able to recite them verbatim, but understand the concepts behind them. Another thing that we're going to talk about is how, again, carbohydrates are going to be our main source of energy. We're also going to get energy from other macromolecules such as fats and proteins, but our main source of energy is going to be carbohydrates. We're going to take that food energy that we're going to eat and we're going to transfer it into our body. And we're going to transfer it and make ATP. Now, think of the energy in these these macromolecules as like money that you can't use. It might be like in the form of yen, or like the American euro. You still have value in that money, but you need to transfer it to the American dollar to be able to use it at like a local store. So that transfer of money is just like the transfer of energy that we see here. One vocab word that is also covered in this section is entropy. This is just the relative amount of disorganization. With entropy, even though you start out with low entropy, you're eventually going to have high entropy, which means more disorganization. I like to relate this to like your bedroom. Even though you might clean your bedroom, there's no way that bedroom's ever going to be as clean as it was once time moves forward. You can see here entropy always increases in a system. I also like to make the analogy between like a new pair of shoes. No matter what you do to that new pair of shoes, you will always have more entropy. There will always be more disorganization in that pair of shoes. They will always become more dirtier, less organized. Even if you clean it, you can never get it back to its original state. Or actually a couple of different vocab words that we're going to talk about are metabolism. Metabolism is just all the chemical reactions within your body. I have a big chart. It's actually behind me here. So if you ever come to class, you can see this big chart. These are a lot of the processes that go on in your body. Check this chart out. It's a great way to show you how dynamic and how just intricate and complicated the intercellular processes are. But this just shows you all the metabolic pathways that are going to be found in cells, or at least a lot of them. This is a chemistry term. These are two chemistry terms we got to know: reactants and products. Reactants are just whatever goes into the reaction. The products is what comes out. We're going to see this a lot within enzyme reactions. So again, reactants go into the reaction. Products are what comes out. Two more types of reactions that we're going to go over, and I'm sure you've heard these before: exergonic reactions and endergonic reactions. These are important for CHS. So if you're a CHS student, you'll want to pay close attention to the next couple slides here. With exergonic reactions, you're going to have a reaction that releases energy. Think about cellular respiration. You're taking glucose and you're breaking it down, you're releasing that energy. Endergonic reactions are the exact opposite. You need input of energy. You need to input energy for this reaction to occur. So you can see muscle contractions, nerve impulses, protein synthesis. You're putting energy into this. So this would be like photosynthesis as well. Now, these are two different charts that we're going to talk about. We're going to talk about activation and energy a little bit today. Exergonic reactions, again, they release energy because energy is exiting the cell, or exiting the reaction. So you can see here how much energy we have in the reactants. Yes, you need to activate, so you're going to be putting some energy in, but at the end, your products will have less energy because the energy was released. Here are these endergonic reactions. You have some activation energy that you have to put in, but again, the reactants have less energy than the products do. So that means you have to put in energy. In this case, you're going to have something called Gibbs free energy. Gibbs free energy is going to be negative for an exergonic reaction and positive for an endergonic reaction. What you can, again, analogy you can make: exergonic reactions, you feel heat because after the reaction occurs, there is going to be a release of heat. Endergonic reactions, it's going to feel cold because you have to put heat in. Think about that heat being the energy, or the energy being the heat in this case. ATP breakdown and buildup is a great analogy and a great example of exergonic and endergonic reactions. You can tell here we have to put energy in to form ATP, so that's going to be an endergonic reaction. To get energy out, it's going to be an exergonic reaction that you're going to have a break of the bond here. I'm just going to fly through this because there's a lot of information here. I want you to take a look at it. Again, forming ATP on this left side, I'm sorry, the right side, right here. ATP is going to be formed between ADP and a phosphate group. You have to put energy in, and we're going to get that energy from glucose and other carbohydrates. So you have a positive delta G. It's an endergonic reaction because you have to put energy in. And again, it says which has more energy? The product has more energy. There's more energy in ATP than in the ADP and phosphate group by themselves. Now, when you break down ATP, you're going to get ADP in a phosphate group. That means energy is going to be released. You have a negative delta G because, again, you have less energy in that reaction. And then you have, it's an exergonic reaction because you're releasing energy. And what has more energy? The reactant. ATP has much more energy than ADP and the phosphate group do than by themselves.